Hello everyone, I'm Dr. Priya Hassan and thank you very much for once again inviting me for your mini winter school, and it's always a pleasure for me to talk to students, and here I go. So since I have two talks, I thought the first one which I'll give you will be more of covering all, some kind of an overall view in astronomy, and which I've called 10 big questions in astronomy. And the second part which I would be doing is I'd be showing you some analysis of data using Kepler, and some of you all can actually try your hands at it. So I will actually show you how to run it, and hopefully you can try out doing some data analysis as part of the workshop. So let's start with my first part, which would be the part which will be about, it's kind of a general overall view about astronomy. And like I told you, one sec, I'll just start. Yeah, so like I said, it's about 10 biggest questions about the universe and how we are trying to answer them, because I thought this would cover a very wide spectrum of things in astronomy which could interest you all, and hence I thought this would be a good thing to do. So, but you could always get in touch with me. My email is there, and if you have more questions, right? So first of all, let's start with definitions. What is astronomy, astrophysics, and cosmology? What's the difference between these three things? Because often people use all these three words and it's not very clear. So astronomy is basically the study of celestial bodies, right? Astrophysics is a science that employs the methods and principles of physics and sometimes even chemistry in the study of astronomical objects and phenomena. While cosmology is the study of the origin, development, structure, history, and future of the entire universe. So in principle, they do overlap in their domains, but this is the basic difference in their focus. So let's see the 10 big questions which I've put forward over here, and obviously the rest you can ask. You can always send the email and ask your questions. So let's start off with the 10 big questions, and here are the 10 big questions. I've listed them, but we'll do them one by one. Okay, so let's start with question number one. Question number one is, can an asteroid fall on the Earth? Okay. Now, if you actually, June 30th is actually celebrated as Asteroid Day. This is a UN sanctioned day of public awareness on the risk of asteroid impacts. Why is that important? Because here what you're seeing is a picture of an impact which took place more than 100 years ago. This is in 1908 in Tunguska. This is Siberia. And you can see that even after 100 years, you can see there's a clearing over here in the forest where you can clearly see no trees, etc. So even after 100 years, you can definitely look at this place and guess that something's happened over here. So we all know that the dinosaurs, right? The dinosaurs went extinct about 65 million years ago. They lived on the Earth for about 165 million years. And then you had a massive asteroid about the size of 10 to 15 kilometers, which impacted that, right? That is this thing. And what is the proof we have about that? Is that if you actually see in geological records, in rocks, etc., the KPG event, this is called the KPG event, the Cretaceous Paleogene period. It's marked by a thin layer of sediment called the KPG boundary, which can be found throughout the world in marine and terrestrial rocks. And the boundary clay shows unusually high levels of the metal iridium, which is most common in asteroids than in the Earth's crust. So you can definitely see that there is this presence of this other material which is there in the crust. And it was actually found that in the Gulf of Mexico, Yucatan Peninsula, there's a Chicxulub crater, which is about 150 kilometers. And this is actually predicted to be the site of the impact of the asteroid, which got the dinosaurs extinct. Now, we also have a similar example in India. I don't know whether you've heard about it. It's called the Lonar crater. There's a lake over there, which is the obvious thing what happens. You can see it's so beautifully round. Look at the picture over here down. You can see beautifully round lake. And this is in Maharashtra. And this is actually, you can see that there was, it is a meteorite impact which took place. And it is one of the only 4 known hypervelocity impact craters. And there are other ones also. There's the 3 other basaltic impact craters are in southern Brazil. And you can see that this crater rim is about 1.8 kilometers in diameter. And now we have a lake over here. So So such impacts do happen. If you actually ask the question, how often do these impacts happen? So every day, in principle, the Earth is bombarded with more than 100 tons of dust and sun-sized particles. Once a year, a car-sized asteroid hits the Earth's atmosphere, creates a fireball, burns up. This is right on top, which is similarly to what we call our shooting stars, right? You see it burn up higher up in the atmosphere. But every 2000 years or so, you could have a meteorite the size of a football field, which could actually hit the Earth and cause significant damage. And once every few million years, you could have something threatening like the one which hit the dinosaurs. And typically, if the rocks are smaller than 25 meters, then most of them they likely burn up before they enter the atmosphere because of the friction, the heat generated, and these are our shooting stars. But if the meteor is about, say, 25 meters to smaller than 1 kilometer, maybe there could be some local damage in the area. But anything larger than 2 kilometers could have worldwide effects. So at 5.4 kilometers in diameter, the largest known potentially hazardous asteroid is called Tortatus. And by comparison, asteroids which lie in the asteroid belt between Mars and Jupiter, they actually pose no threat because they are reasonably far away from it. But you could have asteroids which are larger than even 940 kilometers. So what are these asteroids and where do they come from? So if you actually look at the solar system, right, when the solar system was formed, you have the solar nebula, okay, in which you basically have the sun forming in the center, and you have this planetary debris. This is the protoplanetary disk around the sun, and basically planets form from this protoplanetary debris. Okay, this is how the solar system formed typically. I'm sorry, this video is not working. I don't know why. And what you can see is that typically, if you have debris of this kind, it can, okay, I will do this, and I'm sorry, but I'll go back to my presentation, and hopefully now I will be able to play this thing. So you can see over here, here's the protoplanetary, the protosolar nebula, and here you could have planets forming over here. Okay. Now, while the planets formed, right, there is obviously a lot of debris around, and not all this stuff becomes planets, but there's a lot of rocky debris around, and that is what essentially are the asteroids. Okay, so that's why you have them all over the solar system, from planets which either did not form or broke up. Right now, can they hit the Earth? Obviously, they can. Since the Earth was formed 4.5 billion years ago, there have been routine hits coming from this thing. And like I said, an asteroid capable of global disaster would have to be more than 400 meters wide. And asteroids can strike the Earth, obviously, often enough. Now, what are the ways we think we can save our planet from such asteroid impacts? There are typically three techniques. One is typically which science fiction movies always liked was by doing a nearby, nuclear explosion. That, for example, there's an asteroid coming, you send a missile from the Earth and it bombs it off and finishes it off, right? That's the kind of thing which attracts most science fiction movies. But this is a little, you even split the asteroid. Again, those pieces can further again come and fall on the Earth. And obviously it's not very, it is obviously risky to be putting nuclear material onto a missile and sending it off, right? The other option is what is called the gravity tractor. That, for example, if you actually use a set of massive group of artificial satellites, they are sent to the asteroid, and basically their job is to basically deflect the asteroid from its path. So if the asteroid was on a impact path, you're basically moving it by gravity so that it doesn't come and impact. Another way is also to crash into it, and by crashing into it, not to break it, but basically crashing it onto to deviate it. Okay, and this experiment was already done by NASA. This was done with the DART mission, and in the DART mission, what they did is they basically had this double asteroid, Didymos with Dimorphos, where you had the DART mission which actually hit this the satellite of this asteroid and measured how well we could deflect it from the Earth, and in that way stop an impact, right? So these are the typical three techniques that people this thing. So this is the DART mission I was talking to you about. It was launched in 2021, and basically it went to a binary asteroid and tried to deflect it. So it crashed into Dimorphos at a speed of 6.1 kilometers per second. And then basically what was done is people tried to monitor what was the deflection caused by the impact. Okay. And if you actually see over here, this is the double thing. And because it's a binary, it's very easy to actually measure the change in orbital parameters, right? If you had a single asteroid, it would be very difficult to do that, but with the binary one, you can do it. And that's why it was done with the binary asteroid. So you can see with the coming in of the Dimorphos and Dimorphos, with the transit of this, you could actually see. So it shortened its 12-hour orbital period by 32 minutes, which is a very large amount. The predicted amount was actually 1 minute 13 seconds, but it actually managed to impact it better. And basically, like I said, the job in this is to deflect the asteroid so that it doesn't continue on its path. That's the job. So as long as you do that, it's good enough. You don't need to break the asteroid as long as you deflect it. So that is what is done. So in principle, the DART mission was a successful mission, which actually showed how we can actually deflect it. It did a very good job. Now, like I said, there are different kinds of this thing. They hit us at different frequencies, and depending on the impact energy, this could be like a Hiroshima or Chelyabinsk, Tunguska, and various other this thing, right? So this could give that kind of an effect. So what is basically done about it? How do we detect asteroids? We actually, if you look at images of the sky, what you will see, I'll show you in this. Look at this image of the sky. You can see stars are in their constant position, but you can see that there's one object which is actually moving. I hope you could spot it. That is this object. Look at this one. The sky is moving very fast. All these other stars are on their place. This sky is moving, which basically implies that this is very close to us, and this is an asteroid. So what happens is there is a citizen science project for asteroid hunting. It uses this software called Astrometrica, which actually uses images, real life images from various telescopes which are being used, and users are encouraged to inspect the images to look for moving objects of this kind. So if you could detect a moving object of this kind, then we try to characterize that object, find its orbit and other parameters to actually confirm whether it's an asteroid and what is the orbit this asteroid has. It is a threat. So this is an ongoing citizen science project going since a very long time, where citizens, you, even students of astronomy or even people who do not know astronomy, all they need to do is inspect these images to identify these objects. And in that way, they can identify potential threats that we have. So there is a minor planet center, which actually has data on more than 1 million minor planets in the inner and outer solar system. And if you report it and it is confirmed that it's an asteroid, you will also have the honor of naming the object with the approval of the International Astronomical Union, and studies are made on this to actually check whether there's a threat or not, right? And you'll actually find it a lot on the net, but for example, there was a recent paper of a team of amateur astronomers with literally 3-inch telescopes they used. They found a main belt asteroid, and they actually found its moon, right? So asteroids, so in that way, this is an exercise in actually even saving the planet, because in case this asteroid is a threat to a planet, then it's obviously very useful if you manage to catch it. Let's go to question number 2. I spent a lot of time on question number 1. Let's move to question number 2. How did we find our place in the universe, right? How did we know? You know through astronomy books that, there is the sun and there is the solar system and there are stars and there's a galaxy and there are many galaxies. How do we actually know our place in the universe, right? How did we discover that? So the first thing that we all noticed, which we noticed if you were even a caveman, you would notice that the sun rises in a direction. We call that direction the east. It sets in a direction we call the west. And there's a day-night separation of approximately 12 hours. Okay, this is what everybody observed. So how could they explain it, right? So obviously, in most cultures, it was the sun was in a chariot and the sun comes from here, goes the other side, gets tired, then rests and comes back again. Those are the stories in most mythologies about it. But why does this happen? So we all this thing. Another important thing which people noticed was seasons. Seasons means there is a certain summer, winter, spring, summer, autumn, winter. There was a realization that there's a difference in temperatures. And what people noticed is that the sunrise that took place in different constellations. These groups of stars, we actually joined the dots, gave them some names, called them constellations, and that's basically called the zodiac with the sun moves. And what we noticed is that if there's going to be summer, for example, the sun rises in a certain constellation. In winter, the sun rises in a certain constellation. So the constellations we see in the sky also vary in winter and in summer. And people realized that there was some connection to that, right? The other thing they noticed is that stars move like this in the sky. They rise in the east and set in the west. But then you have these certain objects which seem to loop around. They loop around like this. They do not move like the stars. And therefore these objects were called wanderers or planets because they did not move like the stars. But obviously it was understood that if they are moving faster, then most probably they are closer to us. That's why we can see their movement much better, because a faraway object, you cannot see the movement too well, right? So often the apparition that you have, that the moon is moving with you. That's basically because when you're moving, the distance between you and the moon doesn't vary much. And therefore you get the feeling as though the moon is moving with you, right? So therefore you will also look at it like that. So the earlier model was the Ptolemy model, which actually said the sun was at the center and the earth and everyone went around it. And that was called the geocentric model, right? Now this evolved in what was called the heliocentric model, when various people, for example, Galileo, realized that Venus actually shows phases. And for example, that could be only explained with a heliocentric model, where you have the sun in the center, you have the earth over here, Venus within the orbit, and with different positions of Venus you can get phases, right? And then there were other observations, etc. So you have Copernicus, who actually proposed the heliocentric theory, and there are various reasons, we don't have the time, but why the heliocentric thing actually matched observations of planets, which we were seeing planets moving in epicycles, moving back and forth. So those could be explained well only with the heliocentric model, and therefore we actually see it like that, right? Then people, so the heliocentric came in, and then people noticed the Milky Way as a band across the sky. And then as telescopes came in, so we are looking inside out. So while you're inside the galaxy, it's very difficult to realize that you're within the galaxy. But then there were various people, for example, Herschel, Kapteyn, etc., who tried to make a picture of the galaxy, right? So what Herschel basically did, he assumed that all stars have equal brightness. So if a star is faint, it's basically further away from us. And therefore he made a picture of the universe based on this assumption. And then Shapley actually used observations of globular clusters, and there were various methods to which we could find the distance to globular clusters. And what he actually discovered, that the globular cluster system actually had a center which was not the sun, okay? Which was not the sun, but it was at another position. And this was the position of the galaxy, the distribution of the galaxy, and hence the sun is not sitting at the center of the galaxy, it is away from this, right? So he actually used this. So Shapley in a way is the Copernicus of the galaxy, okay? And then as people used telescopes, there was a world of galaxies, various galaxies observed, and therefore we know now that we live in a universe is huge, and there are many galaxies, of which one is the Milky Way, which has many billions of stars going around it. And of those stars, there's one star called the sun, which has planets going around it, and the third planet around the sun is the Earth, right? So that's how it kind of evolved our understanding of our place in the universe. It's very interesting to actually see how historically ideas developed, right? Because ideas have to develop, number one, using observations, and number two, using some kind of theory to explain the observations. And in science, all these things always go hand in hand. You always have your theory which has to explain the observations you get, right? So let's go to question number 3. We know now that the universe is huge, right? There are loads of galaxies over here. One of them is the Milky Way, which has a sun, which has the planet. So if the universe is so huge, we come to question number 3. Is there life elsewhere in the universe, right? So that's our question. Let's first come to the first question. Are there planets other than the planets of our solar system? And I think many of you all know the answer. These planets are called exoplanets. It's a planet outside the solar system. This is from a science fiction movie, Tatooine, where you can see 2 suns. But obviously, the first step is to look for exoplanets. So how do you look for exoplanets? Essentially, it's very difficult to look for exoplanets, but I think the good part was that there was a persistence. People actually wanted to look for it because there's a very beautiful quote by Carl Sagan, which actually says the universe is a pretty big place. If it's just us, seems like an awful waste of space, right? And therefore, there was a lot of drive in people to actually look for exoplanets. There are various methods used to actually look for exoplanets. We are going to talk about some of them. One is radial velocity. For example, if you have a host star and you have a planet, then because of the tug of the planet, you are going to have the host star going around in an orbit. And because of that, if you actually look at the spectrum of light coming from the star, there's going to be a stage when it is blue shifted, when it's coming towards you, and when it's red shifted, when it's going away from you, right? So you'll actually find a shift in the spectral line, which will give you radial velocity, which is nothing but a reflection of Doppler effect. The other effect is called transit photometry, that if you have a star with a planet in front of it, when the planet comes in the front, the light from the star falls, right? So you will have a certain dip. Another technique is called microlensing. We'll talk about that. That is, the gravitational field of the planet will actually act like a lens and therefore brighten up the light coming from a sun. And the final method, which is already being used, is called direct imaging. That means if you cover the star in some way, you can actually probably image the planets going around the star, right? Now, I hope you're aware, but in the year 2019, the Nobel Prize was awarded to Michel Mayor and Didier Queloz, actually for their discovery of the first exoplanet going around a sun-like star. So this actually came way back in 1995, okay, where they found this planet going around the star 51 Pegasus, okay? And here is the team, the Swiss team. They use a small telescope in Switzerland. You can see the telescope over here at the background. And basically what they use is Doppler effect, delta lambda by lambda is equal to r, radial velocity divided by c. So if you can measure the delta lambda, the shift in the spectral line, you can actually measure the radial velocity. But I want to just appreciate that this is a very difficult measurement to make because, for example, if you just look at the tug of Jupiter on the sun, Jupiter is at a distance of about 5 AU. 1 AU is the distance between the Earth and the Sun, which is called an astronomical unit, 150 million years. And if you actually see the tug of Jupiter, it actually causes this radial velocity to be something like 13 meters per second. So if you were to do delta lambda by lambda for 13 meters per second, you can substitute over here, you will actually see that you need a very, very high precision. You need a precision of this delta lambda is going to be about 10 power minus 14 meters, okay, which is 10 power minus 5 nanometers. That is the kind of scale at which you should be able to measure delta lambda, okay. So at present, the instruments we have, the best of instruments, now with the VLT, this can actually do 10 centimeters per second, but this is in 1995 when they did it for this. Now, the other method to find an exoplanet is called the transit method. That means you look at the light coming from a star. If there's a dip in the brightness, you know that a planet comes in front of it. This can be due to different causes also. If there could be a variation in the brightness of the star or something, or it could be a binary star also, which can cause the transit, but it could be a planet. So, to date, we know about 6,500 exoplanets, and they are confirmed, but there are many candidate exoplanets also. So yes, so the answer to question number 3 was yes, there are planets outside our solar system. And now we come to question number 4. Is there intelligent life in the universe? That means, are these exoplanets habitable? Okay. Now for exoplanets, we define what is called the habitability zone, which is basically the area where water would be in liquid form. Okay. So if you have the sun over here, if you're too close to it, it's too hot. If you're too far away, it's too cold. This is called the Goldilocks zone. While this is the Earth, and Earth you can see is somewhere like this, and this is the habitable zone, right? So we know of the exoplanets which are already known, we know a very large number of them which are actually habitable exoplanets. Like I said, water is in liquid form. In principle, the temperatures are good enough. Now, we are now coming on to James Webb. You all know about James Webb Telescope, and one of the jobs being done by James Webb is actually characterization of exoplanets. So what you can see over here is that what can James Webb do? It can actually see water. Basically, it's going to see spectral lines coming from these exoplanets. So if you shortlist candidate exoplanets, which you find out through other methods, like through the Kepler mission or the TESS mission, you can further do spectroscopy of them with James Webb. And therefore, in the first light photographs of James Webb, you actually had an exoplanet called WASP 96b, and you had the near infrared imager slitless where you actually showed the presence of, this is not a James Webb, this is a Kepler thing, but here you can see this is a James Webb image which is showing the presence of water in this thing. So you can actually then, this is the Drake's equation which tells you about the habitability, and you can actually predict it. So there's an interesting thing said by Arthur C. Clarke. Two possibilities exist. Either we are alone in the universe or we are not. Both of them are equally terrifying. Right? Question number 5. What are black holes? This is what students always love to talk about. So black holes' theoretical definition is it's an area of space-time with a gravitational field so intense that its escape velocity is equal to or exceeds the speed of light. So what is escape velocity? I hope you all know that if you want to escape the Earth's gravitational force, you need to have a velocity which will balance the potential energy, right? So typically it's root of 2 gm by r. For the Earth, it's about 11.2 kilometers per second. If you have that kind of a velocity, you can escape the gravitational force of the Earth. Now, if you do it for a black hole, again, you'll put this with 2 gm, and here you can put it as r, okay? If we put this as c, velocity of light, then this r is called the Schwarzschild radius of this thing. So I put r, this is, if I put this value to be c squared, I can have to have this Schwarzschild radius. Now nature produces black holes in many different ways. We know that the center of our galaxy itself has a black hole, okay, which is here, and the sun, if the Milky Way were to be converted into a black hole, it would have an approximate area of 2 into 10 power 15 with the density of this. The sun would be something like this, the earth, all of these would be something like this. I'll be sharing this with you. You can actually see these if you want to see them in more details. I've got to rush through it because of want of time. But how do black holes affect the things near them? So are we in danger of being eaten up by a black hole? If you're far outside the Schwarzschild radius of a black hole, right, then you don't need to worry. You just have the gravitational field of the black hole which will pull you, and that's it. So you will orbit around the black hole. But if you come within the Schwarzschild radius, then yes, there is spaghettification, you'll be pulled apart and things like that. But if you were to, for example, if the sun were to become a black hole, don't worry. It's too lightweight to ever do that, but even if it does become one, we will continue to being on our same orbit because the mass of the sun will be the same. So then the orbit of the earth will also be the same, right? So in principle, we do observe them through X-ray radiation, which we get in the vicinity of black holes, right? So there are different methods which we have of observing them. Nature produces different types of black holes. There are supermassive black holes, like the one sitting in the center of our galaxy. There are what are called intermediate black holes. There are stellar mass black holes. These are black holes caused by when stars reach their final state of their lives. And then you could even have a micro black hole, which is a small one, right? Which is predicted that it exists. So normal black holes are born, like I told you, through the death of massive stars. So if we have massive stars, they form from a collapsing cloud. You have a star, massive stars, then would burst out as a supernova, and the core of it would collapse and actually form what is called a black hole. So this is the life cycle of stars. We don't have the time to talk about it. So like I said, you could have a supernova blast, and the central part, if it is not very massive, it could form a pulsar or a neutron star, and if it's more massive, it will form a black hole, right? So nature does produce black holes. Black holes do exist, of different sizes and different masses, right? Let's move on to question number 6. What is at the center of our galaxy? This is a very interesting question, and people actually had a big problem answering it, basically because near the center of the galaxy there's a lot of gas and dust. So if we look at optical light, we cannot see anything much, right, in the center of the galaxy. So therefore, but we know that the stars moving near the center of the galaxy, they move with very large velocities. So you can actually use plain Kepler's laws to find the velocity, the mass sitting over there, for which stars move around with such large velocities. And it was then discovered that it's about 4 million solar masses, which is the mass at the center of the galaxy. So in the year 2020, these three people got the Nobel Prize. So Roger Penrose basically did theoretical work on black holes, while Reinhard Genzel and Andrea Ghez, these two people actually did observations of the black hole sitting at the center of our galaxy. Now, how do they do it? Like I told you, the center of the galaxy has a lot of gas and dust, so you will not see it in optical light. But for example, in radio light, what you can see over here, this is the radio image, you can actually see this is close to the center of the galaxy, Sagittarius A. And if you actually see it even in X-rays, it's high energy, hence you can actually see it also in X-rays. So what typically Andrea Ghez, her team did is they used an infrared telescope. They used the very large VLT. And what they did is they observed the motion of S2. S2 is a star which is sitting over here. This is Sagittarius A. This is in this area, this vicinity near the black hole. And they basically, it has a period of about 16 years. So they actually had many, many years of observations, more than 20, 25 years of observations to observe this star so that they could calculate the orbit. Once you can calculate the orbit, you can use that to actually calculate the mass sitting at the center, which will cause this thing to move at these velocities. So this was many years of very laborious observations in the infrared using some very, very advanced techniques, because this is this region which they are studying. This region is near the center of galaxy. You can see this part is zoomed up and showed over here. And what they had to do was basically observe the motion of this star. So this was very meticulous work run over many, many years so that they could actually trace the orbit, right? And you can see that not just S2, but they traced the orbit of various stars in that region. And using that, they actually calculated. So you see, every observation will give you a point on this orbit, and you finally get the orbit. And they calculated that the center of the galaxy has a black hole of the mass 4.3 million M-Sun. And that is why these stars, they actually are moving around with velocities exceeding 5,000 kilometers per second. Just imagine, right? These are crazy velocities with which these stars are moving, but they're doing that because they're going around a massive black hole, right? So life is difficult for them. They have to move with those kind of velocities. So thanks to these researchers, we actually have a very good estimate of what is in the center of our galaxy. Now, why is that in the center of our galaxies? We do not know. A lot of galaxies have black holes sitting at their center, but we still do not very well understand what is the relationship between the galaxy and the black hole. We know that there's a relationship between the mass of the black hole and the mass of the bulge of the galaxy, but what is the role that the black hole plays in the formation and evolution of the galaxy is still an open question. We still do not know that very well. Let's come to question number 7. So what do we know now? How did the universe begin, right? Now, observational data, like I said, we have to basically use observational data. So here you can see a picture of Edwin Hubble at the Mount Wilson telescope. And what Hubble did is he basically observed galaxies, again used the Doppler effect to find out the velocity of these galaxies, okay? And we don't have the time to talk today, or okay. So what was he doing? He was using the Doppler effect. So if you have something going away from you, light gets red shifted. If it's coming towards you, light gets blue shifted. So what actually Hubble found is that, you can see this over here, is that he measured the Doppler effect, the velocity of these galaxies. And then there was some other work by Henrietta Leavitt through which you could measure the distances to these galaxies. And what he found is that there was a direct relationship. The further galaxy away from us, the larger was the velocity which it seemed to be moving away from us, okay? So he got something like this, a plot like this, velocity versus distance, where he fit this. In today's time, that would not work, but he fit it to a straight line to basically show you that as the distance increases, the velocity increased. And this went as a linear relationship where the constant was called Hubble's constant. Okay, and very fast this was given the name of the expanding universe. Okay, that means you have these galaxies moving away from us. So at some point of time, they should have all been at one point together, right? And then after which they started expanding and moving away from us. Okay. Now this was through observation, so you could actually measure the Hubble constant. And the interesting thing is that since you are assuming that the start of the universe was everything was together, you can actually calculate the age of the universe as 1 upon h naught, where h naught is Hubble's constant. And you can actually find out the age of the universe to be 13.6 billion years, right? And that's what we know. So this is the expanding universe. You are in the Milky Way over here. There are other galaxies over here, which are like blueberries or raisins in a cake. If you bake it, then this thing expands. So the Milky Way doesn't expand. You and me don't expand. But the space between us expands, right? And therefore, in that way, you could have the expanding universe. So that is the picture which we got. Another verification of the expanding universe came through what is called the cosmic microwave background, that the starting point is what we call the Big Bang, and it was assumed that if this Big Bang took place, then there should be some relic radiation of the Big Bang, and we actually have detected it as a 3 degree Kelvin radiation, which was measured, and there have been various satellites, one is COBE, one is WMAP, etc., which have very accurately measured this radiation, the background radiation, and variations in the background radiation also. Question number 8, what is dark matter? Now, galaxies, just think of a galaxy. You have a set of stars going around the galactic center, right? And let's say we can measure the rotation of these stars around the galactic center as a function of distance from the center, okay? Now, the central part of the galaxy was like a disk, right? Then you will have V is equal to omega r. So if omega is constant, V is proportional to r. And this is what is called the rising part of the galaxy, the central part, okay? Where you can see that all these stars, V is equal to omega r. This is like Keplerian kind of a thing, right? But then there were, okay, here is Vera Rubin. I love to take her example because Vera Rubin was a remarkable astronomer. What she did is that she was observing galaxies and measuring their rotation curves. So what she found is that through stars, you could get this rapid rise. It was not exactly linear, but later on through radio observations, you got something like this. Now, if you had a Kepler kind of an orbit, 1 by r squared is how the velocity will fall. So typically you should be getting a fall in velocities like this, right? But what Vera Rubin observed is that as you're increasing your distance, the velocity seems to be even increasing. Not too much, but increasing. And if the mass of the galaxy is sitting in the center, then how can it be increasing outside, right? Because like I said, your velocity has to go as 1 by r squared, right? So it should fall down. But she got this thing that it doesn't seem to this thing. And this is one of the most path-breaking things in astronomy, because when she got these results, initially people thought there was some mistake in her observations, right? How can you be getting something like this when we expect to get a fall? But she verified her observations many times, and it was clear that her observations were fine, and therefore she proposed an explanation to her observations, with which she said that the outer reaches of galaxies have matter in them, and that is why these stars have these extra velocities. They are, pushed by that, but that material we cannot see it. We do not see it in any observations, and therefore she gave it the term dark matter. Okay, and using the velocity of these stars, measuring these velocities, again, you can very easily predict what is the mass that can cause these stars to move at such velocities, right? And she actually got those masses, the dark matter mass, for example, of the Milky Way to be very, very large, right? And for example, for the Milky Way, the dark matter mass is more than 90% of it. And similarly, she observed various other galaxies also and tried to measure the dark matter in them. And it was found that more than 90% of the mass of the galaxy is sitting in this dark matter. Okay. Now, this was a very revolutionary idea because, like I said, this is one of the examples where you have something which is totally counterintuitive against the norma. And even today, dark matter is one of the most important questions in modern astronomy. It even leads people to actually doubt Newton's laws. There is another theory called MOND, which is modified Newtonian dynamics, which is basically another theory of gravity saying that maybe at large scales, gravity behaves differently. So if Mond theory was right, then dark matter would not be needed. But in short, it's a very important area of research in astronomy, because it basically tells you a large component of the universe is something you are not observing. It's dark matter, and therefore it's very important for us to actually study it and know what it's all about, right? Because if it's the bulk of the universe. And then to add to complications, I have question number 9, which is what is dark energy, which is even worse. That then people realized with Hubble's data, when they realized that things that, they are expanding, when they started doing better observations of external galaxies with supernovae, with known these things, they realized that the expansion is happening with an acceleration. Can you imagine it? So in 1998, you had two projects. There are two different projects, Supernova Cosmology and High-Z Supernova. Both these teams, they got the same result, that the universe is not just expanding, it is accelerated expansion. Now, for the universe to collapse, you have gravity, which is an attractive force. This is an opposite force, which is actually causing the opposite of it. It's causing acceleration, right? And therefore, it was not understood what is this kind of energy which is kind of the opposite of gravity, right? Quintessential gravity, or various people gave it various names, and one of the favorite names that people gave to it is dark energy. So therefore, dark energy, this is the force which is causing these galaxies to actually accelerate away from each other, okay? And so that's yet another complication as to what is causing this acceleration of the universe. But through observations, we know that this acceleration is there, okay? How do you counter it is the problem. So the Nobel Prize in 2011 actually went to these three people over here, Saul Pertmeier, Brian Schmidt, and Adam Reyes, all of them, for this discovery of accelerating universe, right? And so basically what they used is they used supernovae. So you're doing something similar to what Hubble did, only Hubble used Cepheids. Cepheids have methods to find out their distances, but those are for closer by galaxies. What these people did is that they used supernovae. Supernovae are very bright, so it's very easy to observe supernovae in faraway galaxies. So they used that to actually find the distances to supernovae. And then they used the spectra to calculate the velocity. The same formula we did earlier, delta lambda by lambda is equal to v by c. Find out the velocity. You know the distance because of supernova science. We know you can very well predict what is the distance to a supernova. It's like what we call a standard candle. That means we know what's the brightness of a normal supernova, and therefore we can find the distance to a supernova. So that's exactly what they did. And using this, they used supernova type 1a. Using this, they actually find out this, and they found out that, so yeah, this is a standard candle, and they actually found, this is Hubble's law, but here you can see that there's acceleration. So if you look at these plots, again, this is magnitude versus redshift, you can see that there seems to be an acceleration, which is being caused by dark energy. So this is dark energy, which again we do not understand very well what it is. So there's a lot of this thing. This is like negative pressure, can't be done by matter. It's not dark, just transparent, light seems to be passing through it. There are various probes, for example, the WMAP probe, which actually tries to study the universe, the dark energy, the dark matter, which actually says that 73% of the universe is dark energy, 23% is dark matter, and only 4 or 5% of the universe is ordinary matter, right? So all that we are actually studying is barely 5% of the universe. The rest is all this other material which we do not know. Okay, and now I'm coming to a fun question, which is our last question. Is space tourism the future, right? What's happening? So I'm sure you've at least know, I often when talks I ask people, how many of these people can you identify? And everywhere people identify Elon Musk, who says sooner or later we must expand life beyond a little blue mud ball or go extinct. Carl Sagan, who said all civilizations become either spacefaring or extinct. And Stephen Hawking, who said, I don't think the human race will survive the next 1,000 years unless we spread into space. And therefore, we are all out in space. Earlier, space was all government material, so you had only government agencies like NASA, JAXA, ISRO, Roscosmos, only government agencies who actually handled space, right? But we all know that some time back, there was a paradigm shift. So for example, NASA suddenly decided to outsource their work because they thought that there's a lot of expenditure and research and development for space stuff, So better give it to some companies. But then the companies have to invest their money in research and development. And then once they show their capability of doing things, then NASA can pay them money to do it. So here you have companies whom you've heard about. There's SpaceX, there's Boeing, all these companies who got into space business because that's how NASA promoted it, that if they develop their R&D and they show their capability, then NASA can give them contracts with which they can do various jobs. So the three main people are Elon Musk, you can see here, CEO of SpaceX. There's Richard Branson, Virgin Group, and Jeff Bezos, who runs Amazon. He runs also a company called Blue Origin, and all these three guys are into space business. Now, the global space industry is actually picking up a lot. It will reach about 1.25 trillion by 2030. Startup companies already used 15.4 billion in 2021, and it's been increasing. Okay. So, to promote space tourism, obviously people are scared about the perils to go out in space. So, what these three people did is that they basically went out to space with their friends to show you how they thought it was safe enough to go in space and encouraging other people to do so. So, here you have Richard Branson with crew members Beth Moses, Trisha Bandla, an Indian over here, and they actually went on a space mission in 2021. This is July 11th, 2021. And they actually, I did not mention it, but the definition of space is 100 kilometers. So if you go above 100 kilometers, officially that is called space. Okay, but Richard Branson and all, they went up to 88 kilometers, but that's not too bad. And they experienced weightlessness for about 3 to 4 minutes, and they literally landed back there. Okay, and then you also had Jeff Bezos. He also went out. This was, see, Jeff Bezos is July 21st, while these guys are July 11th. So after 10 days, Jeff Bezos goes out. And what they tried to do is that they took the youngest guy and the oldest person. So they took a young boy, a young person who was 18 years old from Netherlands, and an 82-year-old aviation pioneer, Wally Funk. And Jeff and Mark Bezos, these are the two brothers who run Amazon. They went out on their flight, Blue Origin, and they're actually selling tickets for space flights, which are approaching about 100 million for a flight. SpaceX, finally, they do their thing in style. So they went out in September, not in July, but they went in September. But they actually sent a 4-person crew who actually spent 3 days in orbit around the Earth before re-entering. And they went up to a much higher orbit. They went to a height of about 575 kilometers. This was called the Inspiration 4X crew. And this is higher up than even the Hubble missions. Okay. Now there are lots of Russian space companies, also Cosmocourse, etc., who are there, who can send people out to space. And there are space hotels people are planning, and so there are many more. And there was even a thing about this man from Kerala who went out in space, bought his ticket and went. There was a Pakistani woman who went out. So you can actually buy tickets and go out in space, right? So that's already the frontier, and things are happening there. So I hope I have triggered your thoughts, and you do have more questions. And if you do have more questions, please do write to me or ask me, and I would be very happy to answer your questions. So I would end my talk over here, but like I said, I just tried to cover from exoplanets to the universe to give you a broad idea of how research is done in astronomy. So thanks so much, and see you soon. Bye-bye.